This is the video for section 18-1 in accelerated geometry. We are going to be learning about graphs of sine and cosine today. So the essential question is, what are the characteristics of the graphs of the sine and cosine functions? We'll have 6 vocabulary words today: amplitude, cycle, frequency, period, periodic function, and phase shift. And we're going to jump right in with those. Periodic functions are functions that repeat exactly, so they are exact replicas of themselves in regular intervals, and those intervals over which they repeat are called periods. The length of the period is called the cycle. So for example, some generic functions. This graph here, which is actually y equals cosine of x, is periodic. You'll see that we have our wave right here that repeats itself. And the interval over time over which that one single wave occurs and then starts to repeat itself is known as the period. So this amount here in green, which is the same here, or the same here, that is the period of the function. Now a graph like this is not periodic, because even though it does sort of start to repeat itself over a constant interval, this V is not an exact replica of that one, or of that one, or of that one. So this would not be a periodic graph. It's very easy to find periodic functions. You can simply look at a graph and tell pretty easily whether or not the function's periodic. So that should be easy to answer. So for example, let's look at these two here. We want to identify whether or not the function is periodic. And then if it is, we want to figure out what the period of that function is. So I'm looking here, and I can tell that I have kind of the same image just repeated over and over and over again in number 1 here. So it is periodic. So now the question becomes, how far do I have to go before it starts repeating itself? So I'm going to look at where I am when x is 0. I'm up here at approximately 2. And then I'm going to say, okay, when's the next time that I'm at 2? Well, it's right here, but I can tell that that's not a full period because I haven't gone uphill yet. The next time that I'm at 2 is right here when x is pi. If I trace this, and so I can tell that from this point to this point, I have one full period. That length is from 0 to pi. So my period is pi units. Now in number 2 here, this one does not look periodic to me, because even though I do have pieces that are the same length with an open circle at the beginning of them, they are not at the same y value. So this function does not exactly repeat itself. So it is not periodic. Now the reason that we're even talking about periods is because we're really focusing on sine and cosine today. And you have already done an activity where you kind of explored sine and cosine. If you remember from the unit circle, all of your sine values come from the y coordinates of every single point around the unit circle. So for example here, when this radius is at a reference angle of pi over 3, my y value is square root of 3 over 2. So that would be the value of sine at pi over 3. It's up here at square root of 3 over 2. Same thing over here at 5 pi over 6. My sine value is 1/2. So if I go to 5 pi over 6 on the x-axis, that's the y value of the sine curve. And then you could do same thing with 4 pi over 3, 11 pi over 6, any other angle measure here around the unit circle. If I go find that angle measure, for example, pi over 4, find its y value, that y value right there is going to correspond to the sine of pi over 4, which hopefully you know is the square root of 2 over 2. Similarly, we can graph cosine the same way using the x values from the unit circle. Now, the amplitude of sine and cosine functions is half the difference between the maximum and the minimum values of the function. And amplitude is always positive. It's basically the height of the graph from what I call the midline, or the middle of the graph, up to the highest point, or down to the lowest point. But since we're talking about a height, it does always have to be positive. So for example here, looking at the graph of sine, The middle of my sine graph would be down here at 0, y equals 0. The highest point on your sine graph is at positive 1. The lowest point is at negative 1. So the amplitude there has an amplitude of 1. Same thing with cosine. The midline is at y equals 0. The highest point is 1 unit above that. The lowest point is 1 unit below that. So cosine also has an amplitude of 1. The domain for both sine and cosine is all real numbers because I could substitute any x value I want into either one of these functions and I would be able to get an answer. Positive, negative, decimal, square root, anything. And I could find the sine and the cosine of it. The range for both of these is also -1 is less than or equal to y is less than or equal to 1. And you can write it like that, or you could write it in interval notation from -1 to 1. Or you could write it in words as all real numbers between -1 and positive 1. Anything like that, as long as you get the point across that it's between -1 and 1. The period for both of these graphs, if you look at sine, for example, it starts at 0, and the next time that it goes uphill and downhill and back to 0 is 2 pi units. And then with cosine, it starts at 1, and then the next time that it goes all the way downhill and all the way back uphill to 1 is at 2 pi. And then the amplitude for both of these, we've already said, they both have an amplitude of 1. Now look carefully at these two graphs of sine and cosine. These two graphs are very similar to each other. If you notice, the sine and cosine graphs are really of each other. If I take the sine graph, I lost my pen. If I take the sine graph and I simply shift it to the left by this much, then I'm back at the cosine graph. Do you see that? Similarly, if I take the cosine graph and I slide it to the right, that same amount, then I end up with the sine graph. Shifting it that far to the left in this case would be shifting it left pi over 2. So sine of x is really the same graph as cosine of x shifted to the left by pi over 2 units. So remember, when we go left, we do opposite. So sine of x is equivalent to cosine of x plus pi over 2. That's an interesting point to kind of keep in mind. And that actually takes us into the first thing that we're going to do with our graphs of sine and cosine, which are transformations that affect the amplitude or the period. You can make the amplitude of your sine or your cosine graph change by vertically stretching or compressing it. And if you think about transformations, we input a vertical stretch or compression by putting a coefficient in front of our function. So by putting some sort of a value right there, that will affect the amplitude of our function. That should be easy to remember, amplitude a. Now the period, we can affect the period by compressing it or stretching it horizontally, by making it wider or making it more narrow. And if you remember back to transformations, the way we do that is to multiply by a value attached to the x. Now that b value there does not become the period. But what it does is it takes our regular period, which is 2 pi, and it divides it by whatever that b value is. And it's going to divide it by absolute value because our periods are always positive. So even if this was a -3 right here, my period would be 2 pi over 3 for my new graph. Now, as you get further along into pre-calculus, you're actually going to have to be able to draw these graphs by hand. But for the purposes of just sort of exposing you to it, we're really just going to talk about how to graph them on the calculator and how to notice the differences in them. So for number 3 here, it says to use f of x equals sine of x as a guide, graph the function g of x equals 1/2 sine of 1/2 x. Identify the amplitude, the period, the domain, the range, and all of the transformations. So I want you to go to your calculator, and there's a couple things that we want to make sure are set and good to go. Number 1, you always have to be in radians when you're graphing these. So go to your mode and make sure that your third line here is down here on radians. Then when it is, go to y equals. In y1, I want you to type the parent graph, sine of x. And then in y2, type our g of x function, which is 0.5 times the sine of 0.5x. Now, if you just do zoom 6 in a normal window, it's going to look crazy. It's going to look like a heartbeat monitor almost. So go to your zoom menu. Do you see option number 7? That will automatically format it into a window from negative 2 pi to positive 2 pi and y values from negative 4 to positive 4. So my blue graph here, you'll notice, is our normal 2 pi, our sine of x curve. And then I have my red 1/2 sine of 1/2 x. Having that visual may sort of help you to be able to identify the transformations and the changes in the amplitude and the period and that sort of thing. So now that I have my graph to look at, I'm going to make my list of all the different things I have to talk about, starting with the amplitude. Now, did the height of the graph change? Absolutely. I can tell that the highest it gets, and then the lowest point, if I can see right here, is at y equals negative 1/2. So that amplitude now, rather than being an amplitude of 1, it is an amplitude of 1/2, which you can tell by looking back at the beginning of the function. You see what's multiplied right there? That's my new amplitude, 1/2. Now for your period, you may not be able to look at the graph and tell exactly what the period is, but you can at least tell that it's much more stretched out than our typical period in our regular sine curve. So to figure out exactly what it is, we take 2 pi and we divide it by the coefficient in front of the x right here. So we would do 2 pi divided by 1/2, which becomes 2 pi times 2 over 1. So our new period is 4 pi. So it actually takes 4 pi units to be able to complete one full wave. Look right here at negative 2 pi. If you trace that, the very next time that you have gone all the way downhill and then all the way uphill and back is to 2 pi. So negative 2 pi to 2 pi is one full period of my function. All right, now let's talk about the domain. The domain is never going to change. That's the nice thing about these. It's kind of like the polynomial graphs. Your domain is always all real numbers for all sine and cosine. Now, when we get into the other 4 functions tomorrow, it's going to be different. But domain for sine and cosine is always all real numbers. And then your range, whatever your amplitude changes to, that's going to change your range. And so our range that had been from negative 1 to positive 1, because we have a vertical compression up here of positive 1/2, that makes our range become between negative 1/2 and positive 1/2. So we can write that as negative 1/2 is less than or equal to y is less than or equal to positive 1/2. That could be one of multiple ways that you could write that. And then the transformations, that positive 1/2 out in front acts like any value that's multiplied in front of your function. And that's where our vertical compression by 1/2 comes from. And then the 1/2 inside the parentheses multiplied by the x, that acts as a horizontal compression or stretch. And remember, anything we do horizontally, we do opposite. So for example, since our period went from 2 pi to 4 pi, it actually stretched by twice as much. So we have a vertical compression by 1/2 and a horizontal stretch by 2. So I want you to pause the video now, and I want you to give number 4 a try. All the same questions, but it's dealing with cosine instead of sine now. Okay, so you can see simply by looking at the graph. The blue graph here is my regular cosine curve, and the red graph is 3/4 times the cosine of 2x. Simply by looking at it, I can tell, number one, that it is not as tall as my cosine graph, so my amplitude has definitely shrunk, and it repeats much more often than the regular cosine graph. So my period has decreased as well because less time goes by before it starts repeating itself. So the amplitude, remember, comes from the leading coefficient, so that would be 3/4. Period is 2 pi divided by the coefficient in front of the x, so that would be a period of pi before it starts repeating. Domain for everybody should be all real numbers. And then the range is the negative and the positive of the amplitude, so from -3/4 to +3/4. And then finally we wrap it up with our transformations. We have a vertical compression of 3/4 as well as a horizontal compression of 1/2. And I got the 1/2 by taking the reciprocal of the cosine of the coefficient in front of the x. Okay, so now let's talk about phase shift. A phase shift occurs when you have a horizontal translation of a periodic function. So it's simply just a horizontal translation. Sliding it to the left or to the right is known as a phase shift. So let's look for example here. Go back to your graph and let's look at cosine of x with this time cosine of x minus pi. Let's look at these graphs here. There's my regular cosine curve. There is cosine of x minus pi. So definitely something has happened here, right? I can tell that the height is still the same. It still repeats in the same interval. It's just all of my points have been shifted over. So we're going to go down the list here. We're going to do amplitude, period, x-intercepts. So that's new. Phase shift, domain, and range. Okay, so my amplitude, because I don't have a coefficient here in front of cosine, that's understood to be a coefficient of 1. So my amplitude is still 1 like normal. My period, because I don't have a coefficient in front of the x, my period is just 2 pi because there's a value of 1 that we would divide by, which would leave it as 2 pi. Now, my x-intercepts. You're going to have an infinite number of x-intercepts. So what you want to do is you want to identify the first time that your graph touches the x-axis. So in this case, that would be at this point right here, which if you go back to your graphing calculator and you do second trace and you go to option number 2 for a 0, first thing you'd want to do is hit the down arrow to make sure that it's talking about your red curve here. We'll make that our left boundary over there, and then I want to go to the right until I've passed that first point. So we get for an answer 1.57. And some of you may realize that that point is actually at pi over 2. So 1.57 is equivalent to pi over 2. Now that's not the only place that it occurs. How often does that repeat? Well, it's going to repeat after every curve up and every curve down. So that's actually half the period. So that would be, if our period is 2 pi, that's going to repeat every pi units. So we're going to put plus pi k, and we're going to understand that k is an integer. And if you don't know, the symbol for an integer is a z with a double bar, kind of like all real numbers is an r with a double bar. Our phase shift then is just like sliding left to right. It's whatever value is inside the parentheses there, but we take the opposite. So our phase shift is right by pi units. My domain stays all real numbers, and my range did not change at all because my amplitude did not change. So it is -1 is less than or equal to y is less than or equal to +1. Okay, so I want you to give phase shift a try with sine now. So pause the video and work this problem out. Okay, so here's the graph that I got. The blue one is sine, and the red one is sine of x minus pi over 4. The amplitude stayed 1, the period stayed 2 pi. My x-intercepts are usually at 0 and then every pi units, but this time, since my graph shifted to the right by pi over 4, my x-intercepts became pi over 4 plus pi k, and we would want to write on that, comma, k is an integer. Like I said, my phase shift is to the right by pi over 4 units. My domain stayed all real numbers, and because my amplitude did not change, my range stayed -1 to +1. Okay, so the last thing we're going to talk about are vertical shifts. Vertical shifts are simply just taking your sine or your cosine curve and sliding them up or down. And we do that just like we've done all vertical shifts for years now. We simply add or subtract a number at the very end of the function. So this k value right here would be a vertical shift. So let's look here at this particular problem. 2 times the sine of 2 times theta plus pi minus 5. And if you want to look at the graph, you can. It didn't say in the directions that you had to graph it, but I will type that in really quickly just so that we can have a visual. And remember, where it says theta in the problem, you can simply just put an x because they mean the same thing. And then minus 5. And you'll notice here that I can't quite see it, but that's because I have a vertical shift of -5. So what I'm going to do is I'm going to change my x min down here. We're going to make it a -10. Okay, and so there are my two graphs. Definitely a difference there. I can tell, number one, that it has been shifted. Number two, the amplitude has changed and the period has changed. So let's make a list of different things that we're going to talk about. Amplitude, period, we'll do phase shift, vertical shift, domain, and range. Okay, so my amplitude is the coefficient out in front, so my amplitude is now 2. My period is 2 pi divided by the coefficient in front of my parentheses. So that would be divided by 2. So my period is pi. Phase shift would be the opposite of the value in the parentheses, so that's going to be left pi units. And then vertical shift is the number outside by itself, so down 5. There's absolutely no transformation that could change the domain of these functions, so it's going to stay all real numbers. Now, my range. Because of my amplitude, my range normally would have shifted to -2 to +2. But my vertical shift also changed that. So since it's down 5, take those amounts and subtract 5 to them. This is the easiest way to figure out that new range. So that's going to be -7 is less than or equal to y is less than or equal to -3. That's how I calculate it. I change them first by multiplying by the amplitude and then adding or subtracting the vertical shift. And if you look at this, the highest point here is at -3 and the lowest is at -7. All right, I know the video is getting long, but I want you to try one more. I want you to pause it and give this cosine problem a try all the way through. Okay, so there's our crazy looking new graph there in red. It definitely has a much shorter period. It repeats much faster. And there's been a phase shift and an amplitude change. So going down my list here, hopefully you came up with an amplitude of 4, a period of 2 pi divided by 6, or pi over 3. The phase shift was right pi. The vertical shift was up 4. The domain never changes. And here's my work over here for the range. I took -1 to 1 and I first multiplied it by my amplitude. So that became -4 to 4. But then I added my vertical shift in, so that becomes 0 is less than or equal to y is less than or equal to 8.